Hi, everyone. Welcome to the session. The first talk is Memory Checking for Parallel RAMs by Surya Madhyalagan. I want to note this paper won the Best Young Researcher Award paper.
Hi. Yeah, thank you very much to the committee for giving me the support. This is so unexpected. Okay, so yeah, today I'll be talking about memory checking for parallel RAMs. And first, I'll give a quick TLDR of what this paper achieves. So first, we define a new notion of memory checking in the parallel RAM model. Then we construct some memory checkers in the PRAM model, which match the asymptotic efficiency of the regular memory checkers in the RAM setting, while also achieving optimal parallel depth. And finally, as an application, we construct a maliciously secure oblivious parallel RAM with polylog overhead. Okay, so what's the memory checking problem? So consider the problem where a client outsources a database to a remote cloud server. So now she outsources database and is trying to read to this database. But because the server might be malicious, these responses back might be incorrect. So if the client only has small but trusted local memory, how can she ensure the correctness of all these responses back from the server? Well, we're cryptographers here. The answer here is quite simple. It's just authentication. But this only works if the database were static. So what if the client is allowed to dynamically update the database? So for example, now she can also perform writes to the database. And now when she reads to the same address, she wants to read the most recent version of that address. So she needs to make sure that what's sent back here, for example, is data new and not data. So this is exactly the setup of the memory checking problem. So this was introduced by Blum et al. In 1994. So basically, a memory checker is a layer between a client and a server. So you can think of this as a program that's in the computer, for example. So now that the client sends its read or write operation directly to this memory checking program instead, then this memory checking program sends a bunch of read or write requests to the server and determines some response. So for the correctness property, we basically want to ensure that the memory checker either aborts or only sends back correct information. So correctness here again means that it sends back the most recent version of an address. The second property we want is completeness to make this non-trivial. So basically, if the server were honest, the memory checker should not abort. Okay, so this is the usual setting of memory checking, but it's actually quite natural to consider the setting where there's multiple users using a shared memory. So for example, again, you have many clients using the same database, or you have a computer with many CPUs using a shared memory, or even a distributed computing setup where there are many GPUs computing some algorithm together. And in this setting, it's actually very natural to also want integrity verification. So one thing I want to point out here is that there's actually more modes of failure. So for example, if you have two clients who make a concurrent write to the same address, so one thing a malicious server could do is actually branch this memory. So now there's going to be two versions of the server. And now when both these clients try to read back to the server server could send back data 1 to the first client and data 2 to the second client. So there's this issue of branching. So one thing I want to actually point out here is, maybe the server doesn't actually have to be a malicious server for this to happen. For all you know, this is just a confused server that just made an honest mistake. So you can also think of memory checking as a tool to ensure correctness, or almost like a sanity check tool. So so it makes sense to also want integrity verification in this setting. So yeah, just to illustrate what I mean. So for example, this branching problem that I mentioned, it could just keep happening and happening over and over until you have many different versions of the database. So in some sense, one of the main goals of memory checking in the parallel setup is to have one consistent timeline or one consistent version of the database across all the clients. So this brings us to our definition. So in the memory checking for parallel RAM setup, you're going to have many clients, and these clients are going to make concurrent accesses. So first, because there's many different memory checkers now, we're going to allow for one setup phase. So in this setup phase, all these memory checkers for each of these clients sets up some key, for example, and initializes some state together. But after this, we're not going to allow any direct communication between any of the clients. And this is just to have a general framework for this. So, maybe it's possible that the clients have some underlying secure channel, but I don't want to make any assumptions about this. So for now, we're going to say that none of these memory checkers can communicate after this setup phase. So concurrent accesses just means that at any time step, all of these clients can send a batch of queries to the server. And now the memory checkers in parallel are also going to communicate to the server, and determine some response. Again, we want this correctness condition, but it's a little different this time. So correctness here means that, first of all reads are correct. So again, that means the most recent version of an address. The second property we want is that if there were concurrent writes made to any location on the server, exactly one of them is accepted. So we're going to give the adversary full power here. So I'm even going to say that the adversary gets to pick who wins, but only one person can win. So if you're familiar with the PRM setting, this is actually the arbitrary CRCW setting of computation. So it's arbitrary concurrent read, concurrent write. So again, we have a completeness condition that says that, if the server is honest, then none of the memory checkers will abort. So what do we care in terms of efficiency? So first, we want the amount of space stored by each of these memory checkers to be small. So for this talk, think of it as maybe storing some counters and maybe an authentication key. So this will be O of 1 words or maybe O of lambda bits. The second thing we care about is storage size. So how much space does the online server needs to hold? And again, in this talk, we actually achieve O of 1 blow up. So think of O(n) words. So now we care about work blow up. So think of work blow up as the ratio of the number of arrows in the second part between the memory checkers and the server to the ratio of underlying concurrent accesses. So how much more communication do you need to conduct to support a parallel set of requests? And finally, the most interesting metric to me, at least, is the depth blow up, because this is the parallelogram model. So we have some parallelization capabilities that we want to make use of. So how many steps of computation do you need to execute all of these arrows in between the memory checker and the server? So we want to also minimize the number of rounds of communication you need to conduct. Okay, so this brings us to our results. So first, just to recap what we know in the regular RAM setting, the best known constructions have O of log n work blow up, and this was already shown in Blum et al. And there's also a lower bound of log n over log n communication for some special cases, which most constructions fall into. And this is a result by Dwork et al. So immediately, if you serialize a given PRM algorithm by just saying at every time step, only one person can talk, this actually gives you O of log n work blow up, but it gives you O of m log n duck blow up. So you're really not using the parallel capabilities. So the main difficulty in trying to take these existing constructions and making it parallel is that all these constructions have this tree structure. So you can think of, for example, a Merkle tree. So when you're trying to make any updates to the database, you might end up with many collisions when updating the internal nodes of a given tree. So this is the main difficulty in parallelizing this algorithm. But nevertheless, in this work, we show how to obtain O of log n depth. So assuming one-way functions, we show a memory checking protocol for PRAM programs with O of log n worst case work and depth blow up. So that means every single, to support any single query, any server only has to make log n communication, needs to send log n requests to the server. Okay, I just want to make a point here that is actually shown that this one-way function assumption is essential for memory checking. So if you want memory checking with sublinear overhead, you need one-way functions. And this was shown in a work by Nauer and Rothblum. So as an application of this, we'll consider the oblivious parallelogram model. So you can think of an OPRAM as a access pattern hiding PRAM compiler. So it's like a memory checking compiler type setup, but the goal of this compiler is to hide the underlying access patterns. So there's a beautiful recent work of Asharov et al., which shows that in the honest but curious setting, you can actually achieve O of log n blow up in both work and depth for OPRAM. So, and this is in fact optimal, as they show in Asharov et al. And I guess I forgot to mention this, Larson and Nielsen in 2018. Okay, so as a corollary of our previous result, we actually obtained the first construction of maliciously secure OPRAM with polylogarithmic overhead. So by directly composing our memory checker with the existing OPRAM construction, we obtain a maliciously secure OPRAM compiler with O of log squared n work and depth blow up. The asterisk here is just to say this is not actually worst case because the underlying construction is not worst case. Okay, and the third result we have is that assuming one-way functions, we show an offline memory checking protocol with O of 1 amortized work and depth blow up. So what is offline? So in the offline memory checking setting, we're going to allow the client to send many batches of requests to the server, and do this many times. But during this query phase, the server is allowed to lie, and the memory checkers are allowed to send back incorrect responses. But at the end of the day, there'll be a verification phase where the the memory checkers communicate with the server and determine if whether all the responses back from the server were correct or if some mistake happened. So this is a much weaker guarantee. You just have to figure out if something wrong happened somewhere, but you don't have to know where it happened. So in this setting, basically the construction adapts this counting technique for offline memory checking from a previous work with Nikon. So basically the high level idea is this. Each of these memory checkers is going to store a local counter, which basically counts the number of updates that particular memory checker made. Now you're going to tag every single database entry with a counter of how many times that database entry was updated. And in the verification phase, all we're going to do is check if these two sums are equivalent. And we basically set up our algorithm in a way such that this is actually sufficient. So here's a high level idea of what happens. So this is the setup. So again, all the database entries are tagged with the number of times it was updated. And every single memory checker contains the number of times it has made an update. So now let's say these three memory checkers are trying to write to the same address. And they're all like, hey, pick me. So now if the server were on it, it will pick one of them arbitrarily to win. And the rest of them will get back a signal that their write did not succeed. And now what memory checker 1 is going to do is, because its write succeeded, it's going to write back to D4 with incremented counter 4. And it's going to also locally increment its counter. So both of these are going to be incremented. And it's easy to check that this summation of counter I equal counter TJ is going to be maintained. So this equality is going to be maintained. But there are two main types of attack the server can still do. The first is this sort of spoofing attack. So basically, when all of these memory checkers try to write to D4, it can pretend that none of them actually won. So this violates our correctness condition because we wanted exactly one of them to win if there were concurrent writes. So in fact, it's interesting because this type of attack will not happen in the regular RAM setting, because if you're the only person writing and you say, I want to write to this address, you know you will win. So this is very unique to the PRAM setting. So to catch this attack, it almost feels like authentication is necessary. And basically to deal with this, we basically come up with this quick agreement protocol to ensure that someone has to win this in this setup. So the spoofing attack should not happen. The next is the branching attack, which I've already mentioned before. So now maybe the server says, okay, 2 of you actually won, but they don't know this yet. But the point is that, well, each M1 and M2 both locally incremented counters, but because they're both writing back at the same time to this D4, they can only increment counter by 1. So somehow the left-hand side is only incremented once, but the right-hand side is incremented twice. And because we're authenticating all of these writes, the server is not able to artificially inflate the counter values on the server. So therefore, all you have to do is basically check this equality to see whether the server lied at any point. So this is a very quick high-level overview of the offline checking algorithm. Okay, so I wanted to leave you guys with some open problems. So first, can we obtain a statistically secure offline memory checker for CRCW programs with O1 amortized overhead? So again, to motivate this, before I mentioned there was a spoofing attack, and that seemed to be the main reason why we needed authentication. So at least in the single RAM setting or in the PRAM setting without any concurrent reads or writes, we know how to achieve this. But I don't know how to get this in the case where there are concurrent reads and concurrent writes. The next question I have is, can we use these memory checkers to obtain an optimal maliciously secure OPRAM with OV login work and depth blowup? So in a previous work, we actually did this for the ORAM setting. So that means in the single client setting, by interleaving offline and online memory checking with the existing ORAM constructions. The question is, can we do the same? Okay, thank you very much.
Any questions? Over here.
Can I ask for the online memory checking problem, is the login blow overhead in the depth, is that essential? Because if I think about a hash tree, there's no depth blow up. You just know, you can ask all the questions in parallels.
Yeah, so I think there needs to be, because when you're sort of like aggregating it over the tree, you need to do it level by level so that you can catch any so if a subtree is updated many times, you need to catch it at that root of that subtree. And it feels like somehow you need to do each level at a time to make sure you can somehow collate all this information without too much blow up. I don't know if that made sense, because a subtree could be updated many times. So I couldn't get around this. It felt like I had to do each level of the tree separately. But that's a great question, whether you can do this all in one shot somehow. Maybe you can get better depth blow up if you, I don't know, for example, allow many, like a MCPU underlying algorithm, but maybe like 2 MCPU memory checking algorithm. Maybe it's possible.
Thanks. We'll take other questions offline. Thank the speaker
Thank
again.
you.
Okay, so the next talk is near optimal private information retrieval with pre-processing by Arthur Lazzaretti and Babis Papamantu, and Arthur will give the talk.
Hello. Yes. Good. So thank you, Tal, for the introduction. Right, so this is near optimal private information retrieval with reprocessing. And we'll start by just defining all these terms in the title. So, okay, it seems like not the best with this look. All right, so this private information retrieval, introduced by Cortal and then a series of other works, is this protocol between client and server where the client is given as input a number between 0 and n, we call it x. The server is given an input n-bit string called db, and they exchange a message, after which the client outputs the x bit of db. And for this protocol to satisfy our privacy requirement, we say that there has to exist some simulator A star that can act as the client. And the server cannot tell if it's interacting with this client, the real client, or A star. Okay, so this is private information retrieval, and it's been used as a building block for many different privacy preserving applications. Metadata hiding messaging, private movie streaming, private ad serving. However, all of these run into a sort of fundamental bottleneck with respect to their non-private counterparts, which is server computation. And this turns out to be, as we defined PIR before, inherent in that PIR, as I defined, requires O of n server work. This was shown by Baimao, Ishai, and Malkin in the early 2000s. And so this sort of motivates the study of PIR with preprocessing. And specifically in this work, we're going to consider client preprocessing, where the client and server interact in a preprocessing phase, after which the client stores this hint of size sublinear in n, which it then uses as advice to perform a series of queries. Okay, and so this is our model. And what we show is that in this model, we construct a scheme that can achieve O of square root of n is server computation, amortized, O of 1 bandwidth, and O of square root of n client space on a single server, where these O's are squiggly O's, they're approximate O's, they hide polylog and lambda factors. And this is improving on previous work from Shiaton Crypto 21, which showed the same asymptotics on 2 servers, or by Koring Gibbs et al. In Eurocrypt 22, which showed similar asymptotics, but with larger bandwidth. And I will also mention here that there has been some concurrent work that achieved these same asymptotics from different techniques, and that was presented in Eurocrypt 23. Cool. So our results can kind of be summarized in 2 large blocks. So first, we construct some pseudo-random sets, which I'll define, with the following properties. These sets have a concise representation. So you can represent this set with a key that's much smaller than the number of elements in the set. You can enumerate this set, oh, I guess I skipped the membership test. So you can check if an element is a member of the set fast, in time also much smaller than the set size. You can enumerate the set again fast. Here fast means time proportional to the set size. And the special property of these sets is this adaptability, which means that it supports adding and removing a constant number of elements from the set while maintaining the concise description. And along with this adaptability, we're also going to need this extra property, which is the resulting key also hides to an adversary which elements were operated on. Given a key that, for example, had an element added to it, it cannot tell which elements out of the elements in the set was added afterwards. Cool. And then after this, we show that we can use these pseudorandom sets with special properties to achieve the PIR with the complexities that we want. So for this talk, I'm going to just mainly focus on one, and I'm going to have to refer you to two for our paper for number 2. And I'll just start by saying that Shi et al. In Crypto 21 achieved such sets that had a concise representation, fast membership testing, fast enumeration, with supporting one removal in the way that we want. And we extend it here to support a constant number of additions and removals. Cool. So our starting point is the privately punchable PRF primitive, which is just a tuple of 3 algorithms introduced by Bonnet et al. And then follow-up work by also Bonnet et al. And Canetti and Chen. So it's gen, eval, and puncture, where gen and eval are just standard PRF algorithms, and the puncture is special in the following sense. So this puncture algorithm, for the purpose of this talk, we'll define as follows. It's going to take in the original PRF key and a set of points, a set of P points, and it's going to output a punctured key where the outputs for the points that we input to the puncture algorithm are re-randomized. So we basically, this key reflips the coins, the puncture algorithm reflips the coins for the points that we input and outputs this key, which hides which elements were reflipped. So this was shown to be possible from LWE by the works that I said it before. And so using this, we're going to construct sets of approximately square root of n elements in 0 through n-1, picked from some sampling distribution. And our initial attempt is as follows. For each x in 0 through n-1, we're going to say that x is a part of the set defined by this PRF key k, if and only if f of xi colon equals 1 for all I in 0 to log n over 2. And this definition can be a lot to wrap your head around at once, but a simple example makes it pretty clear. So if we take n equals 16 and we generate a privately punchable PRF key, let's try to check membership for x equals 7, which can be represented in bits as 0, 1, 1, 1. So all the definition is saying is that x is in the set if we evaluate the x and it evaluates to 1, and then we evaluate x without the first bit and it also evaluates to 1, and then we evaluate x without the first 2 bits and it also evaluates. So this is the whole set definition with respect to the key k. And we can see at first that this distribution already satisfies at least concise representation because we represent the set with just a key. It also achieves fast membership because just by definition, we can test membership of a given element in O of 1 time, where this, again, O is squiggly. For enumeration, it's not so clear that we can enumerate this set in time proportional to its size. So this set is going to have size square root of n. But by definition here, we're defining it per element. So naively, we would have to check each element in 0 through n-1. But if you'll notice here, if we start from the bottom and check smaller strings first, so if we start by the strings of size log n over 2, and let's say that 1, 1 evaluates to 0, then we never have to check 3 and 7 and 11 and 15 because they all share this initial small bit string in their membership test. So building on this idea, we can construct a fast enumeration algorithm that enumerates the set also in O of square root of n time. Cool. So what we wanted initially was concise representation, fast membership testing, fast enumeration, and adaptability. Let's look at where we are right now. We have sets with a concise representation, assuming that this PRF key is small. We have fast membership testing by definition. We hand-waved fast enumeration, but we're going to have to settle for that because we want to get to adaptability. So how do we add and remove elements from the set while hiding which elements were removed? And you might get a hint that it's going to use the only property of the PRF that we haven't used yet, the puncturing. So to remove an element from the set, all we do is we take Z to be the set of, okay. Some technical problems. Thank you. So we take Z to be the set of points that define X's membership, and we just puncture this key, initial set key at Z. What this gives us, if you recall the definition of the set, is that with very high probability, we're going to remove this X from the set because we need all this set of points to evaluate to 1. And if we re-randomize them, then very likely one of them is going to flip to 0. And also by the puncture property, we get that this new key hides which element was operated on. However, what we get is also an undesirable property, is that with some small probability, we either do not remove this element or we remove other elements from the set because of that property of sharing evaluations that we looked at before. And in the paper, we show that we can actually handle this quite easily by just appending some extra points here to be a part of X's membership evaluation. And for adding, we use a similar idea, except we use some rejection sound. We just run this puncture algorithm until we get a key which has this X inside the set. Okay, and this sort of assumes that this privately punctured PRF puncture operation is re-randomizable, but Canetti and Chen show that this is possible from LWE. And so what we get again is that this add always adds elements to the set, albeit in potentially a large amount of time, expected square root of n of time. And in the paper, we show how to get this down to O of 1. The punctured key, again, by the privacy property on the puncturing, is indistinguishable from a key picked from the keys that originally contained X. And again, we run into this problem with the dependency, which we say we can deal with. Cool. So what's left to show is we have shown how to either add an element to the set, or remove an element from the set. But we do not know how to make these work together or to make this work for many times. And the idea here is quite simple. We just use C of these privately punctured PRF keys, and we define our set just slightly differently, where membership is defined given a set key K, which is a group of keys now. Membership is just defined as XORing the evaluation at these K keys at the same points. And now we can define additions and removals sequentially on each key one at a time. And we show that this satisfies the appropriate notions of correctness and privacy. So that sort of concludes our building our pseudorandom sets, modulo some details. And for number 2, I'm just going to have to refer you to the paper. Thank you very much.
Thank you. We have time for questions.
Yeah.
So what is the best known lower bound on client space for sublinear server computation?
Right. So I forgot to mention that, but Corrigan, Gibbs, and Kogan in 2020 show that this square root of n computation and square root of n client space trade-off is optimal. So if you, for square root of n online server time, you can get at least square root of n client space in this model, where, so the model assumes that the server does not store any additional bits at the server other than the database.
If I just aim for sublinear server computation, not necessarily square root n, then is there?
Then, right, so it's sort of a sliding scale that multiplies to n.
Okay. I see.
Does that make sense?
Yeah.
We can actually achieve this with this work as well. I just fixed this trade-off to make it simple.
Okay, thanks.
What would it take to get it under other assumptions? Do you have some nice abstraction of, I mean, you have an abstraction, but it's quite complex. Can you reduce it to, I don't know, some kind of programmable homomorphic secret sharing, or have you thought about abstracting what you need from LWE here?
I see. Cool. So right. So this pseudorandom set is the abstraction. It's not clear that we need LWE specifically for this. Yeah, I'm not sure what exactly we would need to abstract away from the LWE. I do know that what we didn't show here of the construction is that the online phase also requires some FHE in order to get these sets to work sort of obliviously, and that's, I think, the main bottleneck right now.
Okay, yeah, thanks.
Thank you. Okay, so the next talk is proactive secret sharing with constant communication by Brett Hemingway Falk, Daniel Noble, and Tal Rabin, and Daniel will give the talk.
Thank you very much for that introduction. So I'm first going to present what proactive secret sharing is. I'm then going to explain why doing it with constant communication is somewhat of a big deal. And then I will present in detail one of our protocols that achieves this in the semi-honest setting, and I'll give a little bit of intuition for our protocol that achieves this in a malicious setting. So what is proactive secret sharing? So normally in MPC, we're used to the setting where we have the adversary is able to corrupt some fixed portion of nodes, but corrupts these at the beginning of the protocol, and they're set throughout the protocol. And this is a good model in many situations, but sometimes we have a situation where corruptions is a bit more like a disease, that the adversary is able to periodically corrupt different devices and keeps corrupting various devices, compromising them, learning their secrets, causing them to behave incorrectly. But also periodically, the devices are able to be refreshed, that the adversary is kicked off of a device, maybe the device is rebooted, maybe a new device is used to replace this device, maybe credentials are reissued. And therefore, the adversary, while they are eventually able to corrupt each member of the system, will only be able to corrupt a certain fixed portion at any given point of time. So this is the mobile adversary model, and security against it is called proactive security. So specifically, we're looking at proactive secret sharing. That is, we want to be able to share a secret in such a way that even if the adversary is able to corrupt M out of N parties in each epoch, they will never learn the secret. So this is a brief summary of previous work in this area. And essentially, every protocol up to this point required order N communication for each refresh phase. That's N communication per participant. Some protocols were able to kind of get around this by batching this. So if L was a batch size, they could have order L, N over L communication per party per batch, per item in the batch. But sometimes you're not really able to batch secrets. So for instance, if the secret is a private key, either for encryption or signing, that is just one set of data. It's not really able to be batched. So ours is the first protocol that's able to achieve proactive secret sharing that's sublinear. And in fact, we're without batching. And in fact, we're able to achieve it with constant communication. So today I'm going to be presenting a protocol that is secure against a passive adversary. And it again has constant communication, and it achieves a linear threshold in corrupted parties. I will also give a little bit of intuition about our protocol that's secure against an active adversary, which again requires constant in-end communication. There's a kappa term for because it involves PRFs, and it has a lower threshold of square root n adversaries, that parties that can be corrupted per round. So I'm going to be making extensive use of this tool in mathematics called expander graphs. Specifically, I'm going to be looking at bipartite balanced expander graphs of constant degree. So let's break that down. So bipartite means there are two parts and edges only exist from one part to the other. So I'll call these the left and the right parts. Balanced means that each part is of equal size. So in this particular graph that I picked, each part is of size 7. It's constant degree. That is, each vertex has a constant number of edges. In this case, that's 3. And now the property of it being an expander is the kind of crucial one that we need to describe. And specifically, I'm looking at the vertex expansion property. So that means if we pick some set on the left and we look at all of its neighbors, and therefore the corresponding set on the right, there is some expansion that has happened. So the set on the left was of size 2, the set on the right is of size 5, and so there was an expansion of 5 over 2. The set has kind of increased by a factor of 5 over 2. So this expansion amount is one amount that we care about, and specifically we would want this amount to be greater than 1, so there has actually been expansion. We also care about how big the set can be and still have expansion. Clearly, for instance, if the set on the left was containing all of the elements, you couldn't have any expansion because the set on the right is the same size. So specifically, the graph on the left, you might think I've just picked 2 very nice vertices that have good expansion, but actually if you were to pick any 2 vertices on the left, they would expand to 5 vertices on the right. So this graph has the property that as long as 2/7 of the graph on the left of any 2/7 of the nodes are selected, they will have expansion 5 over 2. So these are these 2 terms that we care about, alpha and gamma. Now, you might think that I picked this particular graph because it has this good expansion, and I in a sense did pick a particular graph. This graph does have a name. It's called the Heward graph. And if you feel like interested in discrete math, you can look up its relationship to something called the Fano plane. But the general properties that I've described actually exist for all values of n. This was yes, a series of very interesting works by Spielmann et al. Showed that for any value of n, if you have, you can have a constant degree expander or a constant degree bipartite graph that has expansion some constant greater than 1, and that this is true for some constant portion of the graph. So there are relationships between the terms d, alpha, and gamma, but these terms do not depend on n. And this is kind of surprising if you think about it, that you can expand each vertex just as a constant number of neighbors, and regardless of what set you size for any that you choose for any constant portion of the graph, you will get this constant expansion. So this is the critical property that we need. And now I'm going to show how we can achieve proactive secret sharing using this technology. So the way that we're going to do this is we're going to additively divide the secret. So the sum of the SIs is equal to the secret S, and each of the SIs is chosen randomly. And the way that we reshare is that each party additively shares its own share. And so we get shares of shares, and they send that to their neighbors. So explaining a bit more, so the vertices on the left correspond to parties, and the vertices on the right also correspond to parties in the subsequent epoch. So they kind of, we kind of assume that there will only be a certain portion corrupted in the left and a certain portion corrupted on the right. So they secret share their shares, obtain shares of shares, and then the way that you combine to get the new shares is you simply add up the shares of shares that you received. And some basic math shows that the total is maintained. So what about privacy? So I'm going to show that in this particular graph that you can tolerate up to m adversaries. So I'm doing it with small constants just because it's easier to illustrate, but all of these will hold true for constant proportions. And that's the proof in the paper. But I'm basically going to follow through almost the same proof in the paper, but with small constants. So I'm going to show actually that now the adversary can corrupt M in any round, but it's possible that they might learn more secrets than that in a particular round. So if they controlled all of the messages that were sent to someone else, then they know what share that person is going to achieve. But I'm going to show that they will never actually learn this for more than 5 of the parties. So we can show this by induction. So clearly in the first step, they can only corrupt 3 parties, and 3 is less than 5. So they only know the secrets of at most 5 parties. And so there are 2 parties that they don't know the secret of. And now I'm going to show the kind of inductive step of the proof. So since there are these 2 parties that are uncorrupted and their secrets are unknown, also the shares of shares that they send are going to be unknown. And so the parties that receive shares of shares from those parties, those shares of shares will completely randomize the secrets. And so the adversary doesn't know these secrets that are constructed. The adversary may corrupt 3 of these 5, but there will still be 2 of these 5 that have not been corrupted. And so this property that the adversary knew the secrets of at most 5 out of the 7 parties is maintained inductively. So yeah, this is the proof, and the proof in the paper is basically the same, except it's constant proportions. Cool. So I'll give a little intuition for the robust protocol, and so we can use kind of the same idea to achieve something that has robustness but no privacy. So clearly this protocol has no robustness. If a single party sends an incorrect share of share, then the secret is changed and robustness is lost. What we can do instead is have a protocol that only has robustness and no privacy. So this isn't really a secret sharing protocol, but it's kind of a value maintaining protocol that if the adversary is able to corrupt a constant portion of the nodes in each round, they're not able to change this value. So the expander graph also has this this property that even if we say that the majority, so if we have a majority of good nodes on the left by some constant fraction over a majority of good nodes on the left, then a constant fraction will have the majority of their neighbors be good. And so this means that we can have a protocol with linear corrupting a constant portion of malicious nodes that still maintains robustness. And then basically we can kind of combine these 2 protocols where each of these parties in the privacy setting is replicated using the robustness protocol. And therefore we're able to have square root and privacy, and also square root and robustness. It's a bit trickier because you have to make sure that the replicas have the same randomness for their correctedness without leaking. Anyway, it's a bit more subtle, but the details of that are in the paper, and I encourage you to read it. Thank you, and I'll take any questions.
Questions?
So these expander graphs, are those explicit or?
Yes, they can be explicitly constructed and actually constructed in polynomial time.
Okay, thanks.
Any other questions? Okay, let's thank the speaker again.
Thank you.
So the last talk of the session is Improved Polynomial Secret Sharing Scheme by Amos Beimel, Oriol Faras, and Or Lastry, and Or will give the talk.
Thank you for the introduction. So I'm going to talk about improved polynomial secret sharing scheme, joint work with Amos Beimel and Oriol Faras. So I'm going to start with a high-level overview before going into the definitions. So secret sharing scheme is a useful tool in cryptography. Linear secret sharing scheme are useful for applications, but less efficient. polynomial secret chain schemes generalize linear secret chain schemes to a higher degree. And according to the best known secret chain schemes today, we know that linear secret chain scheme are less efficient than degree 2 secret chain scheme, less efficient than general secret chain scheme. So the question that we ask in our paper is, does the share size decrease as the degree of the polynomial grows? And the answer is yes. So the tool that we use to construct those polynomial secret chain scheme is a conditional disclosure of secrets, CDS protocols. Okay, so now I'm going to continue to definitions and some background, starting with secret chain scheme, which was introduced by Shamir Beckley, Ito, Seto, and Shizeki. So in secret chain scheme, we have a set of parties and a dealer D. We also have an access structure, a collection of authorized sets. For example, gamma K, all the sets of size K or more. The dealer holds a secret S, creates random shares and distribute them to the parties. We say that the scheme is correct if every authorized set, i.e. a set in the access structure, can compute the secret from their shares. And we say that the scheme is secure if every unauthorized set cannot learn any information about the secret. So the share size of secret chain scheme, in this talk, I'm only going to refer to a secret chain scheme of 1-bit secret. We denote the length of SI as the share size of party I, and the share size of the scheme would be the maximum share size among all parties. And the main goal would be to construct schemes with small share size for general access structures. So polynomial secret chain scheme, before going to the definition, let's see some motivation. So secret chain scheme is linear if every authorized set can reconstruct the secrets using a linear function. Most non-secret chain scheme with small share size are linear. And we also have a good exponential lower bound for the worst access structure for linear secret chain scheme of n to the n/2 from Babaga and Wilkerson. For general secret chain scheme, the situation is a bit different. So the best known upper bound is 2^585n from Bamel and Neer, upper bound and Neer. And the best known lower bound is linear omega of n/log n from Seymour. So there's an exponential gap between the upper bound and lower bound for general secret chain schemes. So we want to ask two questions. The first is, can we construct efficient nonlinear scheme for a broader family of access structures? And the second is, can we extend the lower bounds for a broader class of secret chain schemes? And we also want to obtain insights for general secret chain schemes. So a good candidate to achieve these goals would be polynomial secret chain schemes, since it lies between linear secret chain scheme and general secret chain scheme. So now going to the definition, polynomial secret chain scheme was introduced by Paskin, Chanevsky, Vedun, and then by Bamel, Tmar, and Peter. I'm going to refer to the definition of Bamel, Tmar, and Peter. So as I said before, is a generalization of linear secret chain schemes to higher degrees. The shares are vectors over some field F of size L. A set of parties, authorized set of parties of size K, for example, reconstruct the secret from the shares using a reconstruction function. In our case, the reconstruction function will receive K vectors of length L and will output 1-bit secret. And we call this secret chain scheme a degree D polynomial if for every authorized set, the reconstruction function is a polynomial of degree D. For example, if D equals 1, then for every authorized set, the reconstruction function is linear, therefore the scheme is linear. Okay, so now I'm going to show a toy example for a polynomial secret chain scheme. So let's say we have two parties, and the access structure will be the set of the two parties, also called 2 out of 2 access structure. The dealer used 3 random elements to create the share. And these would be the shares that he creates. Each consists of 2 field elements. And the two parties together will be able to reconstruct the secret using the following reconstruction function. So looking at the last monomial, you can see there is a polynomial of degree 2, which variables are the coordinates of the shares, which makes this scheme a polynomial of degree 2. Okay, as I said before, we use conditional disclosure of secrets, CDS protocols, in order to construct the secret chain scheme. So CDS protocols was presented by Gartner, Ishikushi, Levitz, and Malkin. In CDS protocol, we have K parties, also called the servers, and we have a referee. And we also have a function f from n to the k 201. Each party has a private input xi, and the parties also know a secret s. In our case, also will be 1-bit secret. So the goal for this for the parties would be to disclose the secret to the referee based on the condition of f, meaning that if x1 to xk is 1 input of f, we want the referee to own s. Otherwise, if it's a 0 input of f, we want the referee to own nothing. So each party sends 1 message to the referee, but in this state, it would be a difficult goal to achieve since f relies on k independent inputs and the parties cannot communicate between each other, so they also hold common randomness. So in this talk, I'm also going to refer to polynomial CDS protocols, which means in this context that the referee reconstruct the secret from the messages using a polynomial function. Okay, so now I'm going to present our result. I'm going to present two results. The main result regarding secret chain scheme. So as I said before, we showed as the degree of the reconstruction grows, the share size decreases. So more formally, every n-party artist structure can be realized by a secret chain scheme where the degree D reconstruction and share size n to the 0.585 plus some constant CD times n, where the constant is order of log D over log D. So comparing that to the previous results, the best unrestricted general secret chain scheme with unrestricted reconstruction have share size to the 0.585 n, and you can see comparing that to our results that our results approaches to the best unrestricted result as D approaches to infinity. The previous best known polynomial secret chain scheme was of degree 2, prior to our work was of degree 2, and share size to the 0.705 n. And there wasn't a result for a general degree D reconstruction. So first improvement that we show in our work for polynomial secret chain scheme is secret chain scheme with reconstruction degree of 243 and share size to the 0.673 n. Our second result regarding K-service CDS. So we show that for every D and every function F, there is a degree D K-service CDS for F with the communication complexity n to the k-1 times constant CD, where the constant is the same as before, or the log D over log D. So again, comparing to previous results, the best known K-CDS with unrestricted reconstruction have communication complexity of n to the O tilde of square root of k over log n. The best known polynomial CDS prior to our work was of degree 2 with communication complexity n to the k-1 over 3. And again, there wasn't a construction for a general degree D for K-service CDS. But there is a lower bound for K-service CDS with the degree D construction from Bamel to Manpeter of omega of n to the k-1 over D plus 1. So looking at the lower bound compared to our results, you can see there wasn't a way for us to avoid the k-1 factor in the exponent. The only possibility for improvement would be in the constant CD. And again, first improvement that we present for polynomial K-service CDS has a reconstruction degree of 243 and communication complexity n to the k-1 over 4, which improves the degree 2 communication complexity. Okay, so now I'm going to show high level of our construction, a very high level of our construction. I'm going to show the construction flow. First, before I'm going to show our construction flow, I'm going to show the construction flow of the best known general secret chain scheme, and I'm going to compare it to our construction flow. So all best known general secret chain schemes today start with a combinatorial structure called matching vectors. Using matching vectors, LVW relying on the work of Vir and Gopi, constructed two-service CDS. From two-service CDS in subsequent work of LVW, they constructed K-service CDS. And then using the reduction of LV and upper bound Bamenian operator, they constructed secret chain schemes from K-service CDS. So our construction flow starts with what we call sparse matching vectors, which are matching vectors with few non-zero entries. Then from sparse matching vectors, we constructed polynomial two-service CDS. Then for polynomial two-service CDS, we constructed polynomial K-service CDS. And then using the same reductions as before, we achieved polynomial secret chain schemes while preserving the reconstruction degree of the K-service CDS. So our contribution lies in those stages. We first define and present construction of sparse matching vectors. Then we generalize the construction of the two-service CDS of LVW in order to use the property of the sparsity to achieve polynomial two-service CDS. Then we generalize the construction of the K-service CDS to achieve polynomial K-service CDS while preserving the reconstruction degree from the polynomial two-service CDS. Okay, so now I'm gonna conclusion and some problems. So I showed in this talk two results. The first one regarding the secret chain scheme, as the degree of the reconstruction increased, the share size decreases and approaches the best known general secret chain scheme. And it's the same for K-service CDS. As the degree of the reconstruction increase, the communication complexity decrease with the same constant order of log of D over log D. So these two results with the known lower bound for for normal case service CDS was is two obvious open problem. I want to talk about the third open problem. So our generalization of the two service CDS gives us the option to enable us to use what we call S1 matching vectors, where at S1 are a large set compared to the previous used matching vectors. And from that, we can obtain a better two-server CDS and two-server pre-protocol for general reconstruction, not non-polynomial. Okay, thanks.
We have time for questions.
So all these lower bounds and upper bounds are in the information theoretic setting, right?
Yes.
And is it like what is known in the computational setting? Like, do we know of better lower and upper bounds?
Computational. Okay, for this I'm less familiar.
Okay. Thanks.
Any other questions? Okay, let's thank the speaker again. And the business meeting is at 4:35. Please come, everyone is welcome.
Hi, a couple of announcements. There is an extra bus from the HSSB and the venue and to the dinner location. So it will be 5:05, 5:15, and 5:20. And there would also be a third bus coming back from the dinner venue. Like all three buses will leave at the same time. So we have a few spare T-shirts. And those who wish to obtain them should show up tomorrow at 8:30 at the registration desk, and first come, first serve. And we don't have any extra larges left. And we don't have at the moment any spare entire set of souvenirs. However, anybody, I mean, the souvenirs of anybody who doesn't show up by 10 o'clock, the last day of the conference, will be handed out also at the registration desk. Yeah, so anything else? No, okay, so that's it for now.